Hi everyone. When I use person identification for tracking a person in a video, I notice that when the person is highly occluded by an object or by another person, I don't want this bounding box to be considered as a reference for the next frame. Instead, I want to use the embedding of the previous frame with good embedding quality. Therefore, here comes a side project of person ID, a person image quality model. I have tried several methods to label the quality of images. Openpose, mean distance between query and gallery, probabilistic face embeddings, and SER-FIQ, unsupervised estimation of face image quality based on stochastic embedding robustness. The first two methods work well, whereas the later two fail in my case. I've tried openpose for labeling the image quality. The openpose model outputs 25 key points, locations, and corresponding confidence scores. Note that from 15 to 25, those key points are quite subtle for person-ready datasets, so I've tried to use only 15 key points. However, the score doesn't change much. Here you can see the pseudogram truth provided by openpose. You can see that for high quality and low quality images, openpose labels them quite well. There are two occasions of low quality. One is the mean of 25 key points confidence is low. The other one is the model fails to detect the key points at all. It will give a float number instead. The medium level images are also labeled well, as better quality images are labeled with higher score. I also tried mean distance for labeling the image quality. I noticed that both query and gallery images quality could be low, and query images quality is slightly better than the gallery images. I compute cosine distance between one query image and all gallery images of the same ID, and then I scale the mean distance from 0 to 1. And 1 minus scale mean distance is the quality score for the query image. This is the pseudolabels using mean distance. You can see that for both high and low quality images, it labels quite well. But for medium level, the score doesn't indicate the quality very well. For example, the first image looks to have higher quality compared with the second image, but it's labeled with lower score. Here are the distribution of openpose pseudogram truth and mean distance pseudogram truth. And these are the AUCs of mean distance, openpose, and random. The x-axis represents the percentage of queries selected for testing, and y-axis represents the corresponding rank 1. We can see that openpose 15, openpose 25 have very similar results, and mean distance has the best and obvious result. However, in my opinion, mean distance not only learns the image quality information, but also the correlation between query and gallery. Because if a person walks along with another person for the whole video, the quality score would be high. But there are actually more than one person in the bounding box, so the quality shouldn't be high. I used ShuffleNet to train the image quality model. These are the prediction results of one model trained on mean distance. The first row is high quality images, second is medium, and third row is low quality images. This is another model trained based on openpose. Here is the prediction results. You can see that some images have a big gap between the openpose pseudogram truth and the mean distance pseudogram truth. After introducing the two successful methods of labeling the image quality, let me introduce two other methods I've tried but failed. Current face recognition or person re-identification achieves success by comparing features in latent semantic space. However, the features learned by the embedding model could be ambiguous, leading to noisy representations. Probabilistic face embedding represents each image as Gaussian distribution in the latent space. The blurry image will have a larger sigma, whereas the distinguishable image will have a smaller sigma. The mean of the distribution will be the embedding learned by the person-ready model. We use the same training set for person-ready and uncertain model. And we don't need to label any training data for the uncertainty module, which is good. The uncertainty module is a network with two fully connected layers, which shares the same input of the bottleneck layer. The idea is to reject images with low quality inputs. The optimization criteria is to maximize the mutual likelihood score of all same pairs, formulate the loss function to minimize its L, where P is the set of all same pairs, and S is defined here. The reason that it doesn't work on our case, in my opinion, is that there are no guarantee that there is at least one good quality image for one person ID. If all images have poor quality, sigma is really depending on the mu locations instead of the quality of images. This is another unsupervised method for image quality. This paper is published in CVPR 2020. It evaluates the quality with robustness of an image. The robustness is based on the embedding variations of random subnetworks of a given model. Image producing small variations has high robustness, and thus high image quality. And if an image has high variation, it will be regarded as low quality. Number of run equals to 100 stochastic embeddings are generated from the model using stochastic forward passes with different dropout patterns. Each of these subnetworks generates different embeddings. The variations between these embeddings are calculated using pairwise distances and define the quality of image. It uses the same face recognition or person identification model for quality assessment task if the model contains dropout. However, this method doesn't work for my case either. So the authors of the two papers, do you have any suggestions or what I should do next? That's all. Thank you.